Good morning, good afternoon, good evening, everybody. Welcome to Wednesday EMinar Day. Gives me great pleasure to have us all listening to Vladimir Puzyrev, and I'll introduce him in a minute. Just quickly go through the lineup of speakers coming up. Next week, we have Kerry Key, who will tell us about his open source code, Mare 2D-EM. And then a week after, we have Randy Mackey of CGG talking on geologically consistent inversion of geophysical data, a role for joint inversion. And then we have a rather unusual one, Nadine Violette. And this EMinar will be in conjunction with KEGS and with Women Geoscientists of Canada. And Nadine will tell us about her career, a culmination of unplanned opportunities. And then Nasser Mekbel will talk to us about his code, ModEM, that is by far the most used code by academics. And Malcolm Sambridge will follow with a wonderful talk that earned him the Benno Gutenberg Medal for AGU for 2020 and the Benno Gutenberg Medal for EGU in 2021, optimal transport and geophysical inversion. And then we follow with a step away from inversion, and Andreas Junger introduces us to anisotropy from basics to 3D modeling. Just to remind you all that you can find all these EMinars all listed on the EMinar webpage, and I encourage you to visit it because it does change as people drop out or as we have to rearrange things. And you can register for an EMinar, and if you register, you'll get notified of any changes. And you can also view past talks and presentations. So finally, you're on a Zoom webinar. So your functions are to change your audio settings, send a chat message, raise a hand if you want to speak. And so at the end, during question and answer, if you actually want to engage verbally with today's speaker, just raise your hand. And then Q&A. And you can please send all your questions to Q&A, not on the chat. And then I will read those out so they get in the verbal record. And the presenter will try, if they're quick ones, he'll answer them on the fly. Otherwise, at the end of the webinar. So today's speaker is Vladimir Puzyrev, who will be talking about EM inversion using neural networks. And Vladimir is a senior research fellow in Curtin University, and he's coordinating deep learning geosciences theme of the Curtin University Oil and Gas Innovation Center. Focuses on AI and deep learning in the geosciences, and particularly inversion interpretation and uncertainty quantification. It's something we don't do enough of in EM. Vladimir's research interests also include computational electromagnetics, numerical methods for PDEs, sparse linear solvers, and high-performance computing. So at that, I'll invite Vladimir to come online and share your screen and take it away.
Okay, thanks, Alan, and thanks everyone for coming to this talk. I hope you can hear me well.
Yes, not a problem.
Okay, thanks for letting me know. So good morning, good afternoon, and good evening to everyone. It's a pleasure to be here. It's a pleasure to speak at this seminar. I personally enjoyed it a lot. So let me share my screen first. Yeah, okay, I guess you can see my screen now and my mouse pointer.
Yeah, that's perfect, Vladimir.
Oh, yeah, okay, thanks, Alan, for letting me know. So today it's a bit unusual talk. We're going to talk about a new trendy topic such as machine learning, deep learning in the context of electromagnetic inversion. So we are living in a very interesting time now, and I'm not talking about the COVID situation. I actually mean that we still have a large influence of the previous industrial revolution, of the third industrial revolution, which is about computing, these communication devices. But also it's the beginning of the fourth industrial revolution. So, and it's industry 4.0 with its major drivers, many drivers from 3D printing, advanced human-machine interface, robotics, autonomous vehicles, self-driving cars, obviously things like big data and Internet of Things, smart sensors, devices, virtual, augmented reality. And you may ask, where is geoscience in this context? So obviously, geophysics and geology are not the main drivers of Industry 4.0, but we can make a lot of use of these technologies developed in our field. So we're not going to review all potential usages of AI and machine learning in geosciences in this presentation, but we just put some light on a few of them, and we will focus on inverse problems. Here is a brief outline of my talk. So I will gonna start with some exciting things. It's new developments in AI and machine or deep learning. I'm going to review some deep neural networks and their fancy applications in various fields. We're going to see some progress in real intelligence, even something which is a bit concerning, but we're going to then quickly jump to applications in geosciences. I will just have a few examples of what's going on in that field. And again, this field is still in its infancy, so probably we just have last 2 or 3 years of active research using the latest advances in AI and deep learning there. And then the main focus obviously would be that kind of stuff in inverse problems. So this would be the main focus of this. I'm going to show some successful examples for synthetic and for some real data, as there are so many questions to answer. So in the last part, I actually going to talk about the limitations, the challenges, and the current trends that are happening here. Okay, so a few words about actually the terminology. So we have a broad area of AI, artificial intelligence, and we have another popular field of data science. And within those, we have smaller fields. So deep learning is something that makes use of big data, and the deep learning is a subset of machine learning, which in turn is a subset of AI. So when we talk about deep learning, we usually mean something which utilizes deep neural networks. And if we compare traditional machine learning and deep learning, usually the main difference would be, let's say you have some classical tasks such as image classification, and you can have some input, and you want to say whether it's doc or not doc. So traditional ML way to do it would be to use feature extraction and then classification based on some feature, eyes, ear, nose, and so on. In deep learning, instead, you're just gonna give it to some AI algorithm, probably a deep neural network, perhaps a convolutional neural network, which will do everything by itself. It's kind of a black box approach, which just needs to be trained, but it can do all these things without manual feature extraction, feature labeling, and other tasks. And it allows to achieve much better accuracy for some tasks, especially image and spatial data processing. So AI has a quite long history. On this slide, I try to summarize some of the most important milestones of this and previous century. I don't consider what's happened before, but actually the term neural networks was coined almost 80 years ago in this paper by McCulloch and Pitts. And we had a long history with all these developments, AI winters, period of this increased interest. And like a couple of years ago, the 3 scientists, which are usually considered to be the fathers of this deep learning revolution, they received the prestigious Turing Award. So it's usually difficult to pick up one event that triggered all these developments, but most people usually agree that what triggered this so-called deep learning revolution was in 2012, when convolutional neural networks called AlexNet won large-scale image recognition challenge, and it was a huge success. It won it by a large margin against all other possible methods, and this triggered development of other convolutional neural networks and then development of many other things as well. So I'm not listing all major events here, but believe me, there are tens or maybe even a couple of hundreds of real nice developments in this field in all sectors. So roughly from 2017, 2018, we see explosion of AI in many fields of science and engineering. I also have to mention that we had a periods of 2 AI winters, so-called AI winters, when there was decreased interest to AI in 70s and end of 80s. So it's not easy to say what's going to happen next. Now we have explosive growth. Obviously, there's going to be there's some hype in the field, but now we have huge success, and AI algorithms are used in many fields of science and engineering. So it's quite unlikely that we will have another AI winter soon. It probably would be just a period of stable development after what we saw in the last few years. So there are three main driving factors behind this deep learning revolution. So the first, of course, would be availability of data. We are living in an era of big data, and deep neural networks can achieve much better performance, much better accuracy when powered by large amounts of data. So contrary to traditional machine learning schemes, which work well for small amounts of data, but then quickly reach the saturation limit, deep neural networks, when powered by big data, can get much better performance. The second driving factor would be obviously new algorithms. There were many nice developments in the actually in 3 past decades, including convolutional neural networks, many developments in recurrent neural networks, training of optimization, regularization, transfer learning, reinforcement learning, and all other fancy stuff. A huge number of papers published recent years. And another obvious thing is neural networks take over other machine learning methods, especially this can be seen after the deep learning revolution in the past 7-8 years. More and more people are using neural networks. And the last but not least driving factor, it would be actually computational power. One problem with these techniques was that they were very expensive to train, which prevented actually more deeper usage of neural networks in the 90s. But 10 years ago, around 10 years ago, with the rise of GPU technologies, and now when we also have different devices, still we have much more powerful GPUs, which can you see from this NVIDIA slide, and we also have CPUs, TPUs developed for these purposes. So now we have enough computational resources to deal with big data and to train quite deep neural networks. Okay, so there's plenty of applications of deep neural networks in science and technology. So if you use social media or any smartphone applications, you're gonna notice a huge improvement in image processing applications, image classification, segmentation. All these tasks are typically addressed by convolutional neural networks. Many things related to imaging and video processing, denoising, in-painting of image and restoration, super resolution also are done by convolutional neural networks. There are now many programs available on your phones or online when you can colorize your old pictures or old photos, or you can increase resolution of old photos, even make videos from photos, and so on, also powered by neural networks. Obviously, there is a field of augmented reality, virtual reality, intelligence as well. So we're talking about AI, artificial intelligence. We can't help mentioning developments of DeepMind. You might have heard about algorithm, which is now the best player in chess, in game of Go, and game of Shogi. It was considered not possible to beat humans in Go a few years ago, but it happened. AI also play video games, play real-time strategy games, play first-person shooters much better than few humans. Again, processing surveillance information in real time, obviously autonomous vehicles, and many other fancy stuff, always powered by different types of neural networks nowadays. The most common type would be convolutional neural network. It's typically used for image classification, this kind of architecture, or for similar tasks. It's very widely used in geophysics, geology now, because of its abilities to work with spatial data. So a convolutional network, this part has several convolutional layers, usually containing some pooling layers, probably batch norm and some other layers. And typically it's attached to a fully connected network when we talk about classification tasks. And then we get some class for different classes. So AlexNet, the first, let's say, powerful deep convolutional neural network, was using this architecture of only 8 layers, which is considered to be very shallow these days. The image classification works, you have an image and you need to assign it some class. And there can be multiple classes, so it can be a simple binary classification problem. It can be a problem like for image recognition challenge, having, let's say, 1,000 or 10,000 of different classes, and convolutional neural networks achieved great success, and every following convolutional neural network was better than the previous one. Another popular task would be actually image segmentation and restoration, another task from computer vision domain. In that case, we usually work with a fully convolutional network. However, now there are different type of architectures as well, but it's still, it remains to be quite popular one. So here we have encoder and decoder architecture. convolution part followed by a deconvolution part, which actually increases the representation, and we get some structured output, which is typically of the same dimension as an input, but not necessary. In image processing, you can get some masks on different channels of the input images. Obviously, this is widely used in image segmentation and autonomous vehicles and all other related tasks, including video processing and so on, so on. So the recent trend is kind of you need to go deeper and you need to go larger. So this plot shows the large number of architectures developed in this field for, again, for image classification, segmentation, face detection, recognition, object labeling, whatever. So significant improvements were done in the past few years. You can see increasing accuracy. So AlexNet, that network presented almost 10 years ago, is here, actually in the bottom side of this graph, and all these more powerful networks which require much more operation in training and in using them. These networks, they show quite similar, the best networks, they show quite similar accuracy on the image classification tasks, the state-of-the-art image classification task. For example, these are results of these two networks, faster arcs CNN and NASNet, which stands for Neural Architecture Search Network. They give similar performance when you talk about image analysis of object detection and so on. This is state-of-the-art things, and other methods which don't utilize CNNs can't beat this at this stage. Okay, so neural networks are not just about image data or any spatial data, but you can also do nice things with text. You probably noticed a huge improvement in translation, such as Google Translate and other translation devices. Those are also powered by neural networks. So on this slide, I show Alice Bobslowski. So she's a columnist for the newspaper called The Robbie Chronicles. And Alice wrote this small essay about the MT method. So it seems to be written well from the point of, let's say, language. I'm not sure if like scientific description would be correct enough. It doesn't look correct to me because like a magnet moves away from the Earth, and maybe some of applications of MT methods, such as detecting magnetic fields of distant planets and like understanding evolution of the solar system. It doesn't look good from that point of view, but the text itself, it's fine, unless you work with MT methods. I'm sure most of you do, but anyway, so you probably can't publish this essay in a reputable scientific journal, but probably it would work well for tabloids. So the funny thing here is actually nothing on this slide except a few sentences is created by humans. So everything that you see on this slide is generated artificially. So starting from this image, so this person, Alice, she actually doesn't exist. So this image was generated by a special type of neural network, which is called generative adversarial network. So namely it's StyleGAN2, one of the latest developments presented by NVIDIA. You can generate many images like that online. There are websites like thispersondoesnotexist.com, or you can generate fake cats, fake art, fake characters, and so on, so on. The text was also generated artificially. So here I utilized GPT-3 text generator developed by OpenAI. So I took from the empty method book that all of you know, and some of you even contributed to. So I just took this two sentence and this part of a sentence, and the algorithm just wrote something by itself. So obviously this machine doesn't have access to internet, so it can't Google at this stage what is the empty method. So it just understands the context and it invents something by its own. So it's like magneto, it must be using a magnet, something related to Earth. So it produces something about distant planets and evolution of the solar system. Well, it's doing its best. And GPT-3 is not the most, it's not the most powerful natural language processing model, because we have also GPT-3 and more models are in development now. So GPT-3 is a cutting-edge language model. It uses neural networks quite deep to produce human-like text, and this text is actually much better than this one. But this is not available to public. It's owned by Microsoft now. If you're interested more on this, I just refer you to this article in Guardian. Half a year ago, they tested this, and there's an article called Robot wrote this article GPT-3, and they again do the same thing. They just write a couple of paragraphs, and then robot produces this text to convince us that robots come in peace. Okay, so GANs are the most, so probably one of the examples when we have the largest progress in AI and machine learning in the last fields. It's really fascinating. So this picture is a famous AI picture from Ian Goodfellow Twitter. So you can see this tremendous progress just in 4.5 years from generating these black and white poor resolution images. And then they came to the first style GAN, which was producing these more realistically looking faces with high resolution. And this is style GAN 2, presented by NVIDIA a year and a half ago. And there is a new improvement called ADA, which produces images in a similar resolution, but just with slightly more details, less errors, and much better variety and diversity in images, which is also important for your training here. So basically, we now reach the stage where everyone can see the potential and in AI, and it actually happened quite fast. So for many decades, we were kind of in this regime. So many people in scientific community and general public, they were a bit skeptical about neural networks and AI because progress there was quite slow, and we were in this kind of situation for many decades actually. And now reality is such that everything is developing very quickly, and we see this tremendous progress which is happening almost every year. We have a better model in many fields of science and technology. And I'm not even mentioning things like generation of art. There are also convolutional neural networks which can create your pieces of art produced by robots. I'm not mentioning generation of music, all the things, playing chess, shogi, go, video games better than humans, and so on. Okay, so obviously this progress raised some concerns about such fast AI development. I briefly mentioned them here. So you probably heard that maybe Stephen Hawking a few years ago, he raised some concerns about AI and said it can be either the best or the worst things happening to us. If this is not enough, then Bill Gates mentioned something similar 6 years ago, and Elon Musk tweeted this in 2017, and he also raises some concerns about AI, even though he actually invests in there like many other people do. So, okay, maybe these scientists and tech magnates, they don't know exactly the field. Let's have a look at popular culture. So what is the image of AI in popular culture? Well, it's not very positive, to tell the truth. And while there certainly are many positive portrayals of artificial intelligence in fiction, in movies, in books, and in other forms of art, quite often AI is shown in a negative way, like here. So quite often AI is something inherently evil, something that wants to either enslave or destroy humanity and do other bad things. So many of negative stories involve the so-called AI takeover. There is few articles on Wikipedia about AI takeover and measures to prevent that. So basically AI takeover, it's kind of AI size and control from its creators, and so on, so on. Okay, yeah, so these concerns do exist, but there are two things to remember. So first of all, obviously, there is a lot of work towards AI regulation. So basically development of public sector policies and laws to promote and regulate this field. We have a National Security Commission on AI in the US. We have cybersecurity centers that govern their thinking in the UK. We have something here in Australia. All European countries have their own regulations, and there is a white paper by European Commission. All other major AI developers and users, including China and other countries, they have some similar regulation here. So it's considered necessary basically now because these measures allow to both develop AI, to encourage the AI development by government and private companies, and also to manage associated risks. Another thing to consider is actually we need to distinguish between the so-called strong AI and weak AI. We need to have this in mind when someone raises concerns about AI things. So strong AI is usually defined by developing a machine or intelligence with the ability of to apply its intelligence to any problem. So it's related to a general problem solver, which was developed several decades ago. And this AI is usually considered as something like consciousness, sentience, and mind. This is strong AI. On the contrary, weak AI, which is often also called a narrow AI, it implements just a limited part of mind, and this AI focuses on one specific task. So when we talk about applications, when we talk about applied AI, when we talk about neural networks or other machine learning algorithms which help us in solving some geophysical, geological, or any other applied tasks, we always talk about weak AI, and it's harmless. Obviously, there's, regulations of these government policies also cover this part, because you can make some ethics, not very ethical things here as well, but it's harmless, this part. Okay, so let's go to the next part of this presentation. I'm just gonna quickly go through this, and then we go to inversion. So we're not trying to make here a comprehensive review of all techniques. I will just briefly mention that the modern use of machine learning, deep learning in this field is actually, it's centered around many tasks. These algorithms are very efficient in data processing, because obviously geoscientists, especially companies, oil exploration, mineral exploration, collect vast amounts of data, and many routine tasks, not just data processing, but also interpretation, can benefit from using AI a lot. We can get rid of a lot of manual labor here. Modeling and simulation side can be improved by AI as well, inversion, which is focus of this talk, but also monitoring, event prediction of unwanted event, prediction of rare events, assessment of risks, and other fields. There are a lot of work been done in past few years and even earlier in these fields. So maybe the most common thing would be a seismic interpretation, because it's very manually laborious task. So the goal of this task is to recognize geologically meaningful patterns in seismic data. Seismic data is very similar to images. So basically it has a spatial connection, or the spatial connection is a time component as well, but it's very similar to an image. And manual interpretation would be, first of all, would be time consuming if you want to do it accurately, and it would be affected by the subjectivity of the interpreter. So you can have 3 interpreters and 5 different interpretations. This example shows state-of-the-art supervised seismic interpretation with convolutional neural networks, presented 2.5 years ago at the SEG. We see 2 slightly different interpretations, but with quite high degree of accuracy here. So maybe it allows to achieve quite good accuracy, and new techniques, they perform much better than this one. But the problem, for example, with these examples would be generation of large amount of labeled data sets. So another approach would be based on unsupervised seismic interpretation, which does not require manual labeled examples. So here we compromise with accuracy. This is an approach that we took last year. It's based on deep convolutional autoencoder, another type of deep convolutional neural networks, which have this hidden representation here and has a certain million of trainable parameters. We compromise with accuracy, but we don't have manually labeled examples, so it's cheaper in terms of manual labeling, creating this database. And the future probably here would be in semi-supervised methods. Okay, I'm not going to mention other fields. I'm just going to say that if you have a look at statistics, well, I believe everyone noticed this quite significant increase in publications in geophysical journals and conferences over the last few years. So I just searched these terms used in titles of the papers and SEG conference abstract, and basically you can see order of magnitude, literally 10 times increase compared to what happened 5 years ago. And actually the inflection point was probably 2018, when you start having AI, OML, or deep learning dedicated sessions and all major conferences, and now it happens everywhere in applications. Okay, so after this a bit lengthy introduction, I hope a bit entertainment, let's go to a more serious task. So inverse problem. I hope you attended previous EMinars. If not, I would just mention that you should check DAX and Collins seminars, which actually consider EM inversion. So I just briefly mentioned the traditional formulation of the inverse problem. So we have the observations, we have uncertainties associated with this data, and we have some approach to forward modeling, which we consider to be reliable enough. And the goal would be to find the subsurface model that gave rise to this data. So the traditional way to do it, here I just mentioned the deterministic inversion. There is another very wide field of probabilistic Bayesian inversion, which I'm not mentioning here, but there are also applications of machine learning there as well, obviously. But deterministic inversion, we minimize this misfit functional. We have data misfit, we have model misfit. Usually it's an iterative process. So we start with some initial guess and we improve it using some learning rate and using some search direction here. So the search direction usually depends on the gradient that we have. Sometimes we can use the second order derivative information as well. Gradient with respect to model parameters can be written, for example, in this way. And here we have quite expensive part of forward modeling, which can be formulated in that way or any other way that you prefer, not necessarily using curl equation, but in any case, this is going to be quite expensive, especially in 3D. You can use final difference, final volumes, finite elements, whatever, but it can be quite expensive on large scale fields. So the main drawback of traditional inversion, well, there are two main drawbacks, but first one would be large computational cost, and second one probably would be its local search method. So everything depends on your starting model, and you can get stuck in local minima and so on, so on. Just once again, go and listen to these seminars if you haven't done so. So let's say we're looking for another way to make it work, and you don't want to be kind of involved with that math physics for the moment. Just let's say you have some data, your observations, and you have your model, which you want to find, and let's say you want to develop some AI algorithm. So intentionally, this AI algorithm is represented with a black box, and quite often is a black box solution, but you want this to capture this relationship between your data and your model, such that you can go from one to another. So you can get your forward stuff going from model from your data, or you want to get some inverse problem solver going from your data from your model. Okay, great. Everything looks fine at this very simple assumption, but if you go deeper, then if it's a deep neural network, then the first question would be, how do you train this neural network? Okay, obviously you have data, so you should train it using your data, but then you have more questions. So for example, is this data good? If it's reliable enough, is it noisy? Is it coming from real source? Is it synthetic? And even more important, it can be, is it sufficient enough? Meaning, is it a kind of big data? Because if you have some serious black box AI solver, you need big data here. And again, this raises more problems on model size. For example, if it's real data, then you don't know your real model. So if it's synthetic, you use some assumptions here. Model, is it real? Kind of philosophical question, but basically, is it realistic enough here? So for the moment, what people do in these first studies, quite often data and model are considered synthetic. So most studies I saw so far, they, in terms of inversion, obviously, they use synthetic models and they use synthetic data, and it's good enough to train AI up to some extent. So there are many other possible questions that come from this, but we just leave them for the future. We're going to discuss them in more detail in the last section, and now we just assume that, okay, we go with this approach and we can see what it can give us. So instead of deterministic inversion, which uses gradients, maybe second order information, and which computationally expensive, so it can run from few hours depending on your dimensionality and your computational resources. I know some examples when it took weeks. I heard about several months been taken just for one inversion, so runtime can be really quite large. So let's say instead we want to use the framework of the so-called deep learning inversion, which can be divided into 3 stages. So first we generate training data. If we do it using forward modeling simulations on synthetic data, it again can be quite costly. It can take again hours or days because you want large data set. Then you need to train your network. Here you would typically utilize a powerful GPU, and it's not so expensive computationally. It usually takes hours or maybe a few days. So the deepest networks are still trained. They can be trained for a week or even more, but you probably won't use this one in geophysical context. And you can use different, more powerful CPUs, TPUs, whatever it is now. And the good thing is actually this stage is done offline. And you can just develop a powerful AI algorithm and you can feed it with all this data. Doing this once, you can then improve it, but nevertheless, this can be done just one in offline stage. And then your online stage, it can be done fast. Real time, less than a second, often like few milliseconds, depending on your model, sometimes maybe several seconds, but in any case, it's real time. So estimation of your unknown parameters from new data, which was not shown to this guy before, it can be done in real time. So before going further, I have to mention that actually lots of neural networks were developed in the 90s. So I didn't expect even myself, I just heard about few things there, but maybe it would be an interesting fact for younger people if they are listening, that many of similar approaches were taken in the 90s. Obviously, the state-of-the-art neural networks were very shallow, and this method was not widely used. At that time, I mentioned here a few works in seismic context, electromagnetic, MT, DC, Borg resistivity. Apologies if I'm missing something, but there are also these nice review papers. If you want to learn more about these periods, they had a huge number of nice ideas. The problem is that the state of the art of neural networks of AI was not developed that much at that time. And actually, I noticed that all these papers, they come from 90s or like beginning of this century, but there was also some developments, maybe not published even in the late 80s. At that time was unfortunately the second AI winter, so it was not a very fashionable topic and it didn't attract a lot of attention. So obviously algorithms based on neural networks, they probably were marginally applied in geophysical context, and preference was given towards deterministic or Bayesian methods or even other global search, for example, global search methods, like swarm optimization, whatsoever. Yeah, okay, so let's go to modern approach to neural networks and big data. So the state-of-the-art approach is to use deep neural networks, and they belong to the class of data-driven methods. So it's appropriate to use large amounts of data for training these neural networks. So typically what people do is they split all data in training set, which is used for training. Some split is done to validation set and some done to testing set. These proportions can vary a lot. And actually, if you have a lot of data, you won't use this a bit old-fashioned thing, and it's not strictly necessary to use validation set. In some cases, you can avoid using that, so you can use 99% of your data for training, and then you can use your 1% just for fact-checking, and you can use new data to check the performance on real data when it comes to. So, and the goal of the machine learning algorithm, if we talk in general concept, is actually to reduce, let's say, what is called the expected generalization error or expected generalization risk. This is a model ability to adapt properly to new data, new in sense it's previously unseen data. And sometimes people mention that actually this new data comes from the same distribution as the one used to create the training data set. So this is quite important correction. We're going to discuss this on future slides. But basically, we want our neural networks to be effective across the range of various inputs. So if you saw some machine learning papers, you probably see these algorithms when people are trying to stop training not too late, because here we have overfitting and here we have a sweet spot, this ideal sync when generalization is expected to be almost optimal here. So yeah, sorry. Yeah, just a few features of the method based on neural networks, inversion based on neural networks. If you want to, if you didn't encounter it before, so we don't use regularization in its traditional meaning. Instead, training set. So we train every single training set, and ideally it contains realistic models. And your network or your algorithm learns how to reproduce similar models that fit the data. So what you would usually, where you use regularization, you can get similar effect by compromising, by using different loss functions and by choosing properly your models, which have to be realistic, obviously. And the same with sharpness of models is now also determined by training data and by loss function and by some other parameters that you use in traditional inversions, commonly used by regularization as well. You don't have similar concept of regularization here. And you also don't have similar concept of starting models that you would have in traditional inversion. Optimization in terms of neural networks usually means training of neural networks, and it involves somewhat similar optimization algorithms. So contrary to traditional inversions, they usually mini-batch. So instead of using like all data or just using one data like in stochastic gradient descent, we use a mini-batch, maybe 50, 100, a few hundreds of samples per each iteration. And these algorithms are ADA grad, ADA delta, ADAM, Nestor of momentum, ADAM, and other more sophisticated, but usually their performance, in my experience, performance of these three, it's quite similar. So it's not, it doesn't make a big difference here. Okay, let's go to some examples here. I think we have some Q&A. Actually, I will answer this after the after we go through the last part here. So yeah, so it's an example of 2D EM inversion. You might saw this couple of years ago in Geophysical Journal International. So basically, it's an approach based on convolutional neural networks where the data is created through synthetic 3D models. So we generate 20,000 of models. We also make benefit of symmetry to reduce computational cost. And we use deep neural networks having up to 10 million of parameters. So I utilize here this fully convolutional architecture when we have some input, which is our measured data, and we have a structured output, which is our unknown resistivity distribution. So in that case, the main benefit was that we can predict new data here basically in a few milliseconds. It was in the context of monitoring. Yeah. Okay. It was in the context of EM monitoring of CO2 plume located deeply in the subsurface. We get some different variants of receiver distribution. We get this measured fields, which ideally would be measured in a grid-like fashion, or they can be measured just along lights, which is more realistic. And we need to predict the model. So basically, this fully convolutional network gets this or this as an input and outputs your resistivity distribution in just one plane. So it's 2D inversion in that context. So we start here with the let's say yes or no configuration where we have just like a background with slightly varying resistivity, or we just have a target, which is our CO2 plume here. And here we see different scenarios from the test models. So these models, they were not shown to the network during training, but they are similar. They're coming from the same distribution, and we see quite nice accuracy here. So black lines here shows the actual CO2 plumes, and red is actually the distribution of predicted. So this is the closer this is to one, the better intersection over unit, but we see quite nice accuracy here, except maybe a few of them. So everything depends on the size of your training data. When you have just a few hundreds, then your average accuracy will be quite low because many would be just bad predictions, like this one, or actually quite worse. But when you increase it to 20,000, or this number used in training here, you get significant improvement in your accuracy. So it's a bit obvious in all machine learning big data applications. More data you have, usually better accuracy. Not always, but it's usually. We can also determine actually the distribution of resistivity. So in this case, we are predicting not just plume or background, but we try to determine actual resistivity. So this is ground truth. This is estimations with convolutional neural networks. Again, we see quite large, quite small errors in terms of mean square errors, and quite large in terms of IU between these elements here. And another good thing about this method is actually it's quite robust to noise. Everything which is based on convolutional neural networks is usually robust to noise. So here we have some examples with white noise of different levels, and you can see that IU deteriorates quite slowly. Maybe with this high level of noise, we see large deterioration, but until that, it's quite robust to noise here. Okay, let's quickly over this example from 1D EM exploration. This is work with Andrei Svidinsky. We have recently paper in Computers in Geosciences on that. So here we use similar concept, but with 1D CNN in exploration. And because we use 1D forward modeling codes very fast, we parallelize them. We can easily generate as many examples as we want. So we generate 500,000 of different examples for frequency domain CSEM. We generate a smaller database, 10,000 for TEM, because the model is slightly simpler there. And we tried to estimate the resistivity of, in this case, it's going to be 150 layers for CSEM or 50 layers for transverse electromagnetics. These are synthetic scenarios which represent marine CSEM case. You can see that the method can get similar performance when you get some resistivity targets to it. So if there's a deep conductor, you can't see it using 5 frequencies, but again, it's shadowed by this resistor. It's probably not really possible using CSEM. Again, few 1D models stitched together give some kind of similar pictures with not so large difference. The method also performs well on real data. So this is data that was kindly provided by this company in Denmark, WACHEM dataset. And here we can compare the conventional inversion using Levenberg-Marquardt method. In this case, they just inverted for 5 layers, but boundaries of layers were not fixed. So you have 5 resistivities and depths and thickness parameters of each layers. And here we have the same 9 and 5 profiles using this method. So we created a synthetic data for this survey setup following a sufficiently large collection of resistivity models. And you can see that convolutional neural networks based inversion provides quite similar results. So here we use just a fixed depth layers. We have 50 layers, but still results. Obviously, there are some differences here, but these conductors and resistors, they match quite well with the conventional inversion on this real data. And again, this is fast, obviously, because it's 1D, but this is real time because it's neural networks. Okay, a quick mention on seismic inversion. So this is work we did a couple of years ago. Similar approach used to impedance inversion. So again, we generate a large set of models with velocity varying around almost 4 times to represent all these possible geological formations. We had more 1D layers. Individual layers are more difficult to catch here because there's a large number of layers. When it's less than 100, it's more precise. When it's more than 100, you need larger data sets or maybe slightly different techniques, but the general trend is quite similar for true models. This is a synthetic example, and for predictive models, they mesh quite well. And again, stitch 1D models show quite similar results here. And training data was just 80,000 of examples, which was limited by non-parallel algorithm in that case. And a bit on like optimizing convolutional neural networks for FWI. So this is what we did last year. So we use again full convolutional neural networks in context of seismic inversion, 2D seismic inversions as synthetic examples. We have quite nice resolution here, if I'm not mistaken, 200 by 200, so for 40,000 of potential parameters here to get for. We also can see the activation functions itself for each of the channels inside convolutional neural networks, and the models here, they were just some background with varying velocity and density, and we were able to get these estimates. So it's definitely not the same accuracy as FWI, but again, it's instantaneous. So in context of FWI, this can be used as a starting model. After that, you get quite nice approximation to your original model, and you can introduce more frequencies, and you can run your conventional FWI to get these features that detected with better accuracy here. So in terms of deep learning inversion, again, this also can be improved here, but more training data is required, and we need higher complexity of models. So here we just had very basic features, not realistic here in this crosswell scenario, but this motivated us to go further and actually to consider generative models to create largest training data sets for algorithms that are using inversion and some interpretation tasks as well. So we're using here a 3-dimensional stratigraphic modeling frameworks called Badlands, and we create large training data sets with that. So it's data sets of 2D density and stratigraphic models. Basically, I leave out all details, but we generate this data, which comes from this data extracted from simulated 3D models, and which looks like realistic layers having stratigraphic features, and we train a deep generative model based on this data, and basically these examples are generated by a neural network. So we can control this, we can control type of the images generated, we can slightly control accuracy and the diversity of these features, but basically these images, these density images, they are similar to these models used in training, and these stratigraphic models, they're quite similar to those used in training. And you can generate many of them within a second. So it's a cheap way to generate large training data sets if you want, let's say, use density models, so if you want to use stratigraphic models and assign some resistivity, for example, or other properties on these layers, and give it to your algorithms to increase their accuracy and their generalization on models that are almost realistic here. So it's about to be released. It's going to be on GitHub soon. Just follow us and see what's happening here. It will be released quite soon. It's available to everyone to use pre-trained network or to use this data for your own purposes. Okay, and I briefly mentioned that actually you also can generate data as well. So you have a lot of seismic data, but you can generate even more. So these two images each shows 240 so-called tiles of seismic data. It's horizontal seismic data collected at Northwest Shelf of Australia. It was an internship project with us. And basically one of the set is the real seismic data, and another one, just guess which is which, but one is real and another one was generated with a generative model. You can zoom in afterwards, but it's quite difficult to see the difference unless you know some features which come from this. It looks quite realistic in terms of data as well. Okay, and finally, you can use similar techniques for any parameter estimation problem. So not necessarily inversion in context of geophysics, but also any parameter estimation, any inversion problems in physics, geochemistry, like in these examples, or whatever. So we used deep neural networks to identify anomalies and predict missing data in geochemical data distributions. So basically, we used a large database containing 45 samples, geochemical samples. There are many sparse elements, obviously, like in any geochemical data, but we were able to predict elements, missing elements from the rest, because there are some element correlations there. So it works quite well for base metals, nickel, copper, zinc in this example. You can predict some other methods there, especially in this range where you have the most elements. It's more difficult to predict rare events on this side of spectrum, but in this general range, accuracy is quite high. It also works on a spatial scale, let's say. So in another example, we just used all data from Western Australia in training, except this region, which we used as a test setup, and we were trying to predict the distribution of an unknown element from geochemical data, which was kind of assumed to be missing. So here is a prediction of nickel in that region. So it's a true nickel distribution. We have this data, but when training network, we kind of pretended that we don't have. So predicted and true, they coincide quite well. You won't see much absolute difference. So absolute difference would be large, where you have large nickel content in elements, which is obvious. And if you have a look at this, so symmetric mean absolute percentage error, which is relative error, it's usually below, let's say 50 of a maximum of 200 in that case. So only you can see a few tiny spots like this one, or this one. It exceeds 100%, but usually it's quite small, which shows there's a lot of correlation, a lot of hidden information that you can get from these data sets. Similar technique can be applied for classification. So sorry, it's again about rock types, which we were considering in the last year. So we're using same database. There are many rock types associated with this sample. So there are like more than 100, but we reduce them to 10 basic types, and we run classification analysis using neural networks. This is a confusion matrix, and you can see that most of these types are determined quite well. And if you have a look at precision recall F1 score matrix for the test data, they actually look quite good. We have some misclassification of intermediate rocks, which we actually expect, because intermediate Again, it's a human factor. It's classified between mafic and felsic rocks, and the same is undetermined. And F1 score for things when you have many values, like in this regular, it would be quite large. We're very close to 1. Again, inversion in terms of classification have a quite nice precision, quite nice recall, and also F1 score of 0.89 can be quite used in geochemical data analysis. So it's not just parameter estimation, but it's also classification to, let's say, 10 classes is an example, or even more. Everything depends on our data. So finally, as I mentioned before, it's critical to use appropriate data in training this kind of algorithms. And here we are going to talk about some limitations, some challenges, and future trends happening here. So again, everything works quite well when all your data comes from one distribution. So I saw many studies, many examples, research papers when people just generate one data set, split it somehow, and they show that model trained on these two can be applied here. But what happens if it's not? It's a major issue, actually. Again, we have a question of generalization. How generalizable is your model? So is it efficient across a range of various inputs? So let's say if you have only tomatoes in your test, if in your training data, then your model going to see tomatoes everywhere. So any round object, any red objects, or red and round objects will be classified as tomato. And if you want something more, something better, you must consider a large set of representative training models. Again, the models, you don't need to train them on all possible subsurface models. This would be impossible, obviously, for even in 1D case. Just we should train them on a sufficiently large set of representative models, and it will be able to learn the required mapping by itself. Again, there are some tricks can be done. For example, I was showing the example of seismic inversion previously. So when we used previous version of this algorithm, this was the performance on the test data when the models, so they were not using training, they were unseen previously, but they're kind of similar to the training data. So all of them have between one and these two features of different depths, different thickness, but just these two features. Again, okay, performance is quite okay for this kind of problem. But when we gave different distribution, which was totally different from training data, again, like similar features, but more training features, having higher, potentially higher or lower velocities, having some things like not have lateral bounds. Before we make some fixes in convolutional neural networks, we got these results. So after we changed the architecture, we were able to get actually this making on this producing similar results which were shown before. But the point here is model selection. Your training data selection is super important, and using some primitives like people often do in 2D or 3D inversion, some cylinders, some boxes, maybe not sufficient because real geology can be much more sophisticated than this one. Okay, so there's some potential about generalization around the survey setup. Again, this is from EM Inversion paper. So instead of using this grid-like training setup of receivers, they were used in training like that. In test setup, I put them randomly. We use smaller number of receivers, but again, everything is very spatial connected, and because fields are quite smooth, we don't see a significant decrease in accuracy. So full input, blue boundaries, and reduced input, red ones are not very much different, and they're not so much different from the two models. So obviously, we see some small decrease of accuracy, but it's not significant here, again, because of the property of convolutional neural networks. So basically, we decrease the number of receivers, important points, let's say here from 4,000 to 900, and we don't see large decrease of accuracy. And same happens actually when you see, well, when you use 1D lines, few tens of receivers here. Okay, a few more things to consider in terms of using neural networks, training, and so on. So we need to find optimal hyperparameters for each case. They can be selected, for example, guided by validation error during the training set. You can use different types here. The goal is to just avoid overfitting to your training data, which is super important. Different stopping criteria can be used here. Again, significant progress in neural networks can be achieved using transfer learning. So basically, it's copying model and algorithm that is already known to perform well on some other task, and is studied extensively in that field. And it's happening quite often. And also some successful transfer learning examples from, like, let's say, image processing to geosciences. You can develop new loss functions instead of standard ones tailored for your tasks. There is a question of explainability, visualization, also uncertainty quantification, and so on, so on. To just mentioning briefly hyperparameters. So we have a classical case. Let's say this is a classical U-shaped case of your risk of your validation error, where you have the sweet spot, and you should probably stop training here when you have your models to be able to generalize. It was noted by some people. I refer to this paper about reconciling this actually classical bias variance trade-off, because it was noticed that in some cases actually this is a bit unusual behavior. So this curve, this double descent curve, as they call it, incorporates this zone, which is a classical regime, and this zone when actually predictors to the right of this threshold, they have zero training error, but also your validation error somehow decreases, and there is the discussion in the community why it's happening and when it's happening. A few things about loss functions. So performance of the method can be significantly improved by tailoring, let's say, existing new functions to your problems. So the question is how you define model similarity. In traditional inversion, you're going to have your data misfit and you're going to have your model misfit. So during training, you don't care about your data misfit. Of course, you can check it, but usually what people do is just see difference between model parameters, and what we commonly use, just use some kind of root mean square error, absolute error, intersection over union if it's like image segmentation or related tasks, and so on. And also cost entropy losses for classification problems. But often a problem-tailored loss function can improve the performance of the method. For example, IOU loss can work well for image segmentation tasks, but in context of geophysical, geological inversion interpretation, you probably won't say these two models are much different because they have the same shape and they're located quite close if it's a vertical section, but the error is very large. So your accuracy is very low, while in this case it's actually larger, but your models, they look a bit ridiculous here. So it won't work if you have a vertical section here, for example. You need something more related to your stratigraphic, maybe geological picture here. You don't need to disregard physics. Definitely, everything shouldn't be just data-driven. There are many work done within simulation community, for example, the so-called physics-informed neural networks. So people just present neural networks that are trained to solve supervised learning tasks, and they respect physical laws described by nonlinear partial differential equations. And there's a lot of things done in improving finite elements, for example, deep Galerkin methods, another approach similar in spirit to classical Galerkin methods. These people use the solution, they basically approximate the solution by a neural network instead of a linear combination of basis functions, and this can be done, and it actually is done in geophysical modeling as well. So combining neural networks and physical laws, or just making a data-driven approach entirely. Again, and even if you have some skepticism towards purely data-driven based inversion, you don't need to make everything just entirely data-driven. So developments from machine learning, deep learning field can be easily used in your traditional inversion scheme, deterministic and Bayesian as well. For example, again, I refer to this broader scheme of meta-learning methods. Actually, they show you can learn some update function, or you can kind of learn update rule. So there's one recent paper, it's a very broad field with probably thousands of papers during the last few decades. Funny paper a few years ago, learning to learn by gradient descent, when they talk about so-called learned neural optimizers. So instead of using math here, actually you can make this guess by using data-driven methods, and these people show that their learned optimizers compare favorably against state-of-the-art optimization methods. Okay, and just few words about visualization. So it's a black box, but there is some work towards explainability of AI and visualization of what's happening inside. For example, this company, I refer to this article, Inside AI Brain, when they visualize some complex neural networks and see what's inside there. Uncertainty quantification, I'm not mentioning it here, but again, it's another very, very broad scope. I saw some research done in that field. It will be extremely important also from a point of view how reliable these models are, because you have many neurons, you have some connections between them, you have maybe dropout, other regularization techniques, and what's happening if something goes wrong. We have to be confident in these estimators. Obviously, we can always get the data misfit after we get estimations of this model, but uncertainty quantification is super important in this case as well. Data uncertainty, model uncertainty, it just not mentioning this in this talk for lack of time, but it's quite an important thing. Okay, so AI and machine learning in particular are definitely one of the most exciting fields of this century, of this decade and the following decade. It is a game changer in geosciences. It's actively used during the last 2 or 3 years, and it's going to be used more in more traditional frameworks. So the typical use is in processing interpretation, especially data processing, data denoising, super resolution, and so on. People start using it in modeling in inversion as well. So optimistic look at, we are expecting a huge rise in all our traditional algorithms. In inverse context, you can use it in instantaneous parameter estimation. Sometimes for a complex problem, it's not sufficient enough. You need to have a very large data set. So you can start just with a fast decision making. If you need to make fast decision, it's instantaneous. And you can, if you have a very complex model such as FWI, you can just get cheap starting models for your conventional inversion, and you can produce several of them and run several frameworks, several local searches to get several models and maybe try to quantify uncertainty or get some insights into this distribution. Obviously, you can improve traditional frameworks by incorporating AI into optimization algorithms or in some other ways. There's a lot of potential in joint inversion and uncertainty quantification. I was mentioning there. So in more general context, so where should we use AI and deep learning? The short answer would be actually everywhere where it's just justified by your task. So whenever you have big data, you should consider it spatial connected data, images, videos, or any geophysical, geological, whatever, climate data, satellite data, it would work perfectly. Time series data, maybe seismic signals or any other time events used in healthcare, used in finance extensively. Spatial temporal data, any complex dynamic process can benefit from using special type of deep neural networks. Text analysis, any control problems related to robotics, self-driving cars, whatsoever, uncertainty quantification, risk analysis, and so on. So it's not so difficult to start if you're familiar with programming at some stage. There are plenty of free frameworks. So TensorFlow is now combined with Keras, 2 popular frameworks, and PyTorch is also a great framework. So I recommend using one of those, and all examples that done previously were used using these frameworks. One thing to mention, actually, AI is changing the society. So this fourth industrial revolution will have a similar effect to previous ones. There was a prognosis by Bank of America. It happened before the current situation, and it was kind of in 15 years, around 800 million jobs would disappear. And now actually this number can be even larger, because in post-pandemic world, we would expect that people will be more happy to delegate their responsibilities to robots. So this number can be even larger. And when I was giving similar talks to students, I was asking them, let's guess how job market would look in 5 or 4 years now. So these are the most common jobs in Australian oil industry and mineral industry 6 years ago. So probably in 4 years, we will have data science everywhere. We have it now. So all people doing engineering, geoscience will be required to have some maybe small, but let's say literacy in data science, like now computer literacy is required everywhere. Okay, I would like to express my huge thanks to organizers of this seminar, and especially to hosts. Thanks a lot, Alan, for hosting me in the morning, as well as to other organizers of EMinars, to my research collaborators, to organizations that supported this, and finally, thank you all for your kind attention.
Well, thanks very much, Vladimir. That was absolutely wonderful. It was extremely enlightening. I got a huge amount out of it. We have already 3 questions. Perhaps we could just go through those. And if you have any more questions, please start throwing them in the Q&A. So the first question is from Jae Kim, and asks one that also I think everybody watching will be asking is, would the performance of the AI model be limited to what it has seen in the training data? How do we make sure we have covered all possible geological environments in the training data sets?
Yes, that's actually a very nice question. So yes, performance of AI, maybe it's not really 100% limited, but yeah, your output would be similar to what your input was. So your estimations, your predictions would be quite similar to your training data. So there are some ways to introduce noise when it can be beneficial actually for your output. So I wouldn't say that it's 100% limited by your training data, but it will be very similar. So it's not possible to be exactly sure that you cover all geological environments in your training data. So we did some effort towards that in this slide. So we just tried to generate some oops. Yeah, close this for the moment. So we were trying to generate some realistically looking 2D examples, because everything that we did manually was not that sophisticated. But of course, ideally, you would need to create a large bank of real data, and again, depending on the task, if it's inversion, it's more difficult because you don't know the underlying model. But you need to have large training data sets, ideally of real data, to make sure that your that algorithms perform well on your test data as well.
Yeah, I think the issue is a lot of we often don't have a lot of training data sets for some of our, mineral deposits, for example, particular mineral deposits. So yeah, but I really think this is the future. A fabulous talk, and I really think this is where we're going to be going. But the cautions you've expressed, we have to keep in mind. So Syed Mohammed Abdi asks, how can you guarantee that the results of AI are not biased by overfitting? There's no way to go through the black box and find if a mistake happened. It is not always possible to check the final model with traditional inversion approach. Does it mean that we have to trust the computers?
Yeah, well, thanks. Again, we trust computers in most of the things that we are doing. Traditional inversion is covered by math and physics. So it's usually possible to check the final model because you have an estimation of your parameters. And if you have a traditional inversion code you can run, if it's expensive, you can still run your forward model, and you can generate your data. You can generate your data on your prediction with neural network, and you can compare to. So obviously when your data misfit, because between your observed data and your prediction of your neural network is quite large, then something went wrong, and it's obviously not a nice prediction. But in practice, it happens quite. It's not very often, let's say, in that way. So yeah, so there are many things to eliminate this black box bit of a problem, including explainable AI, including uncertainty quantification, and so on. So to make sure that it's not biased by overfitting, that's why people often use different cross-validation sets and other measures. So I would say it's basically a combination of all safety measures. In that case, just checking training models in the proper way, trying to avoid overfitting, make sufficiently large data set of very large representative models, and obviously checking your data misfit on the models that we obtain. And if there are any problems, we usually consider retraining things just to avoid overfitting.
Yeah, excuse me. Craig William Christensen asks, you mentioned the release of the code for GANS that generates synthetic geological models. Who or what organization on GitHub should I follow to access the code when it's released?
Yeah, okay, so now we develop it in private repo. I believe it's either in my profile or it's one of collaborators, but it's in private repo. Maybe the easiest would be just to follow us on LinkedIn. I think the link is provided on EMinar, because when we release it, I will mention it on LinkedIn as well.
Brilliant. A follow-up question from Syed. Are the models you showed are all results of supervised learning approaches? If yes, is there any study that shows a comparison between supervised and unsupervised approaches? Oh,
thanks. Actually, a very interesting question. Yes, so all studies show in context of inversion. They come from a supervised context. This bit I was showing in seismic interpretation, that's actually unsupervised. And sometimes this boundary between supervised and unsupervised, it's not clear because you have semi-supervised stuff. So again, look, this is example of completely unsupervised seismic interpretation. It's just not, which actually analyzes kind of textures in these images. So it's not that exact as a manual interpretation. You don't see this exact these horizons, but it's quite rude on fascias, but still you can see the most common features. But if you put here, if you add here horizons and so on, you're going to see better improvement. In this case, unsupervised, they have slightly worse accuracy compared to supervised state-of-the-art techniques, but they come at much cheaper cost in terms of creating large label data set. And everything that is actually powered by generative adversarial networks also typically GANs on the unsupervised part of that. So again, depending on how you treat this, how do you treat this encoder-decoder architecture, you can consider there is a supervised bit and there is unsupervised bits there as well.
Brilliant, absolutely brilliant. Well, thanks very much, Vladimir. You've answered.
Thanks, Alan.
Yeah, thank you. And so I'd like to, on behalf of everybody, you had an excellent audience, 60 people listening in, and then a lot of people will surely watch you on YouTube. So let me just get back the screen and finish with reminding everybody that the next EMinar is next week at 1500 UT from Kerry Key. And so at that, I'll say goodbye to everybody. Thanks again, Vladimir, and have a good week. Bye for now.
Thanks a lot. Bye.